Thank you all for being here and for your continued support of the IMRR UNESCO Chair SIMR Webinar Series. It's my great pleasure to welcome you here today for this section. And then we are really privileged to hear from Professor Paul, a globally renowned expert in hydrology and flood risk analytics. As you know, Professor Bayes is a professor of hydrology at University of Bristol in the UK, and more importantly, a pioneering leader who has refined how we really simulate flooding and assess flood risk by integrating high-resolution remote sensing data with 2D hydraulic models. His model, List Flood, probably it's the world's most widely used 2D flood inundation model today, and then making a profound impact on both research and practical flood management. Beyond his technical achievements, Paul's continued contribution have been recognized worldwide. He's a fellow of the Royal Society and also AGU, and he has received numerous international awards. His work has not only advanced our understanding of flood risk, but also inspired and guided new generation of researchers, including, I think myself and my group. Today, Paul will share his latest research on simulating 2D hydrodynamics at 30-meter resolution for the entire planet. His presentation will last for about 40 to 45 minutes, followed by the Q&A section. Please feel free to submit your question in the Q&A chat box at any time, and I'll pick them up at the end. Before hand it over to Paul, let me quickly highlight our next webinar, integrating the role of nature-based solution in indicator-based assessment, which will be delivered by Professor Fabrice Winault from the University of Glasgow. I assure you it will be another interesting and exciting talk. I hope to see you there. Finally, a quick reminder for the SIMR 2025, which will be held in Chengdu, the hometown of Panda, in September. Please remember to submit your abstract and help spread the word among your colleagues. Now, without further delay, let me hand it over to Paul. Paul, now it's your floor.
Thank you very much, Guiha. Well, firstly, thank you so much for inviting me to speak today, and also congratulations on the UNESCO chair. This is a huge achievement and extremely well deserved. I can think of no other person who deserves this more. So congratulations on that, and for you and your team for organising such a dynamic seminar series. It's really, really impressive. So let me just share my screen, and we should hopefully then get. Okay, so hopefully you guys can all see this, and we can start the presentation. So today I'm going to be talking about some work we've been doing over a number of years, which has involved applying two-dimensional flood inundation models to the entire terrestrial land surface. And of course, this is a huge undertaking, and it's not something that I could do on my own. It's not something that anyone could do. So there is a big team who have been working on this for very many years, just some of whom I'll mention here today. So when I present all this information, it's really thanks to the efforts of these people. And some of these people work in my teams at the University of Bristol, and some also work for a company I founded called Fathom, which was set up about 10 years ago with PhD students in order to generate these kinds of analytics for use in the insurance and finance markets. So let's talk a little bit about global flood models. And this really has been a rapidly emerging paradigm. And you can see on this screen our efforts at building global flood models from our first go in 2015 through to what we published last year. And you can see how over time we've moved from really quite coarse and clunky looking 1 kilometer resolution models all the way up to the latest versions, which are 30-meter spatial resolution, simulating multiple return period events over the entire planet. And, when we published the first model in 2015, we looked at this top plot and thought, wow, well, look at what we've done. This is fantastic. But if you look more closely, you can see it's quite a poor simulation. You know, the flood appears and disappears along the river valleys. It's quite a coarse resolution, which is then downscaled. It's rather, it doesn't look like real flooding, and there's a lot of tributaries missed off. So over time, we've refined the terrain data, we've refined the resolution, we've refined our estimates of where river channels actually are, and a whole bunch of other things to end up with the final, our latest modelling down here. And here you can start to see we're correctly, or more intuitively correct simulation of flow in the tributaries. You can see the geomorphology on the floodplains now, which is really nice to see. And if you zoom in, there's quite incredible detail here. So how's this done? How do you build a 2D model of an entire planet? Well, I mean, the little secret is that you do it in the same way that you'd build any other two-dimensional model. So the challenge is really to automate and scale the process of model building. But at heart, it's just like any other 2D or 1D modeling study that one would do. So here's the flowchart, and you can see it's got the basic kind of components that we would see in any other study. We've got at the center in box 2, we've got this hydraulic model here, which in our case is list flood FP. So we have a hydraulic model, it needs a DEM, it needs to know where the river channels are, it needs to know the channel dimensions. The model then needs some boundary conditions, and those come from either river gauges or flood frequency analyses, just in the usual way. We might want to take into account climate change, and therefore we take climate change factors from the CMIP5 and CMIP6 models. And once we've done our modelling, we might then want to take into account flood defences, and we might want to project those simulations into the future. But at its heart, this is exactly the same 2D hydraulic modelling, 1D hydraulic modelling that many of you will have been taught in your undergraduate degrees or pursuing your research studies. The skill is just to scale it up and automate it, because we clearly can't manually build models for the whole of the planet. And instead of one single model, the other thing is we build individual models covering 10 or 20 kilometers of river reach. And we do that for blocks of river section across the whole planetary surface. So it's not a single model. Think of it as a patchwork quilt of many tens of thousands, even hundreds of thousands of individual 2D models, all built automatically with globally available data. But at the heart, what we're doing then is simulating dynamical flood inundation. And this is an output from just one of those many hundreds of thousands of 2D models, in this case over a site in the UK, the River Severn and the confluence with the River Avon near Tewkesbury. So this is the kind of detail that you get at 30-metre resolution, and in many places this is a reasonable match to the flood inundation extent. But we'll come on to validation in a little bit. But just to note that we're not just building one model, we're building many thousands, hundreds of thousands of models just like this. This is a few tens of kilometers of river reach. And then we stitch them all together, and that makes our global maps. So how do we do that? How do we make that whole calculation chain, that workflow, operate globally? Well, you need a number of things in order to be able to do it. One of the most important is a model structure that's going to work well with the kind of global data sets that we can get. Globally, we don't know very much about river channel geometry and bathymetry. And we also want to decouple the resolution of the channel widths from the overlying floodplain grid. We don't want a fully two-dimensional model at global scales, because then we would have to have very fine resolution to capture the river bathymetry, and therefore the computational costs would balloon. So 1D, 2D hybrid structures are really the best approach for simulating at global scales. And then within that structure, we're going to have a really fast numerical scheme, because even with high performance computing, these computations take months and months on thousands and thousands of computer cores. In our case, we use the list flood numerical model because That's one we write, and we're familiar with it. But any 2D model would give you similar results. They might just be a little slower. One of the advantages of ListFlood is that it is really blisteringly quick. The numerical solution is pared down to the absolute necessity to simulate dynamical flooding. And we simulate this equation on the bottom here. This is the local inertial form of the shallow water equations. So this is the shallow water equations without convective acceleration. And for most floods, those are gradually varied with flows less than a Froude number of 1. And this is the cost saving by moving to an inertial scheme compared to full shallow water is quite substantial. So we have a continuity equation. This is the equation on the top. We have a momentum, a flux equation, the one on the bottom, and we use those equations over a grid of square cells because that's the most computationally cheap way to run the code. Nevertheless, we still need to deploy high performance computing. So we make use of networks of many hundreds or thousands of cores in order to run these simulations. And we've clearly spent a lot of time optimizing the solver in order to work on the very latest numerical computer architectures. In particular, this paper here by Jeff Neal, just through software engineering of the model code, we got a 10 times speed up in the performance of the model compared to the one that we previously had. So software engineering, harnessing the latest computer architectures, can make a real big difference to whether these simulations are feasible or not. And lastly, we need to put that all into some kind of automation framework. We can't individually build models in hundreds of thousands of locations. We need to write computer code that does that for us. So just to put this in some kind of context, the numerical engine is perhaps a few hundred lines of code. It's a loop over a grid. It's calculating some fluxes and then updating the water levels in cells according to the continuity equation. So pretty straightforward. In fact, the flux calculation is one line of code. And even if you put that in all together with input and output and some checking and things, you only get a few thousand lines of code. The automation framework, on the other hand, is really complex. This is more than 100,000 lines of code to download, automatically build models, send them out to high performance computing, gather the results back and post-process. That is where the effort and the I guess the IP resides in this process. Then data. Obviously, these models need data. Most importantly, we've known for some time that terrain information is one of the most critical determinants of inundation model skill. Most of the global data sets we can get hold of are digital surface models. So they're usually constructed with satellite radar, interferometric radars, and they sense the top of surface artifacts and not bare earth. That clearly is not going to build us a very good inundation model. And therefore, at the kinds of grid resolutions we can simulate globally, what we really need is a digital terrain model. So we spent an awful lot of time taking global flood inundation models and cleaning those up in order to get back to bare earth. I'm very fortunate I've had a couple of colleagues who have been absolute genius at doing this, one of whom is my colleague Dai Yamazaki from the University of Tokyo, who built a DEM dataset called MERIT, which I'm sure many of you will know about. So here we see the Mekong Delta and this peninsula in Southeast Asia. And this is shuttle radar topography mission, 90-meter DEM before correction. And you can see the stripy artifacts. You can see vegetation. You can also see urban areas as well. And this is Dai's cleaned up MERIT DEM after that correction. And you can see that there's a huge amount of error being taken out of the dataset. More recently, my colleague Lawrence Hawker has made something called FabDem, which instead of using shuttle radar data, has used the Copernicus DEM. And he's also in this correction removed the buildings too. So FabDem is the latest, and there's paper. Our latest 30-meter global DEM data is currently under review in press, and it's going to be called Fathom Dem, and we've updated the previous FabDem by using some novel machine learning approaches using image transformers in order to improve even further the DEM skill. So that gives us our terrain data. We're then going to need to know where all the river channels are. We can't go out and map those, so we're reliant on global hydrography data sets. Unfortunately, here too, there have been a number of developments over the last 5 to 10 years by some really bright people. Dai Yamazaki again with the hydrography to go with his MERIT digital elevation model. And also George Allen and Tamlin Pavelski and their global river widths from Landsat data product. And again, hydrography is a really tough field. It's much harder than DEM creation, and I'm very grateful for the efforts of these amazing scientists to give me the data, the tools that I can then use for my modelling. Again, this is an area where there is considerable ongoing further development, and this is areas in which skill is improving really quite rapidly. Right, then we've got our bathymetry, we've got our river channel locations, we've got the DEM, we need some boundary conditions. And here we're taking, we need to estimate extreme flows, rainfalls and coastal water levels everywhere over the global river network or planetary surface. And the way we do this is with some old school hydrology, with regionalised flood frequency analyses. We've had these techniques for the best part of 60 years. And most national hydrology organisations have a version of these methods for their territories. The trick here has been to take those old school methods, but to apply them globally with global data sets. And this is some work by my PhD student, Gang Zhao, that he did for his PhD while he was in Bristol. And this is taking a whole bunch of global catchment characteristic maps and coming up with regressions between those characteristics and extreme flows in global gauge data. And if we can develop those relationships, we can then extrapolate to places which we don't have gauge flows. These relationships vary by climate region. We can also do a similar thing for global rainfall intensity, duration, frequency curves, or coastal water levels. And here you can see in the diagrams the scatter between the observed 1 in 100-year return period flow for a group of catchments and the simulated flow using Gang Zhao's methods. And you can see we've got a pretty good one-to-one line, even though this is a log-log plot. So this is a Q100 in different climate zones. It then turns out we end up with a relative mean bias of less than 18% for all flood magnitudes using this method. And when you think about our ability to actually measure discharge, that's getting close to the error in observed extreme flow data anyway. So I think we're reasonably happy with these methods. Another input data set that's really tricky to capture, but we've made a lot of progress on, is global river bathymetry. Currently, there is no feasible way of measuring this using remotely sensed data. And globally, we have really limited data on river channel shapes and depths. So instead, what we do is we developed a series, well, my colleague Jeff Neal developed a series of algorithms for estimating river channel bathymetry for our large-scale models. And first of all, we make an estimate of the bankfall discharge, what the bankfall discharge frequency along a given reach should be. So for natural channels based on geomorphic theory, you would expect that to be a 1 in 2 year return period flow. And where we have flood defences, clearly the bankfall discharge should be the same as the flood protection standard. So based on that estimate of the return period of bankfall discharge, we look up the magnitude of that discharge based on the regional frequency analyses. And then we use a gradually varied flow solver and an least squares nonlinear optimization to come up with the bed profile that would best recreate the water surface implied by that river discharge. And that allows us to come up with a river bed, which, although might have some bias, will at least go out of those river channels will then at least go out of bank at the correct frequency, or at least the frequency at which we want them to do so. If we estimate the channel depths, the channel capacity, and the return period discharges independently, there is a very great risk that you have a mismatch in those. So either one is too large and the other too small, or vice versa. So this is a way to collapse two uncertain variables, channel conveyance capacity and the return period of bankful discharge. This collapses those two uncertain variables into one. It's one of the key secrets to getting these models working. Then, by doing that, by treating bathymetry as a parameter, effectively, actually, when we start to look at the appropriate frictions, it brings the frictions much more into line with what one would expect from the estimates from, say, for example, Venti Chow's book from 1959. So by correctly estimating the bathymetry, we we let the friction be more of a friction parameter and less of an effective calibration parameter that doesn't have such a strong physical basis. Then finally, just to wrap things up before we get on to the results, we're going to need some flood protection standards globally. And here, Paolo Scozzolini and colleagues have produced this database called FlowPros. It's not perfect, but it's the best thing we've got for estimating the global flood protection standards in different territories. And we might also want to have a look at some climate change factors. And here, for different flood drivers, rainfall, river flow, coastal water levels, we used different climate projections from the CMIP5 and CMIP6 climate model ensembles. And you can see these are the change factors in those quantities. So how much 100-year discharge, 1 and 2 year rainfall, or sea level will change into the future. Greens are increases, browns are decreases, and you can see this complex spatial pattern. It's not the case that discharge or rainfall goes up everywhere. I mean, rainfalls pretty much go up everywhere. Discharge is a much more mixed pattern. It's also a mixed pattern for sea level. Mostly it rises, but if you get close to the poles, actually you see sea level decreases compared to the present day, just because of the nature of how the Earth system works. So here's the model. So this flood FP is 1 arcsecond resolution, and it uses all these data sets that I've just been talking about in order to produce the results. And here's what it looks like. So this is Houston. This is a 1 in 100-year coastal flood event in the year 2020, because we can project both current conditions and project those into the future. And so by 2050, with some sea level rise, with some changing river flows, here's the 1 in 100-year flood extent for Houston if we took no further flood defense actions. And so you can see the level of detail that we can get and the granularity, and the idea that we can project these flood maps for any climate scenario for any time horizon into the future. We can even have an ensemble of those with this. So okay, all very clever, lots of smart people over a long period of time pulling together data sets and model structures. The obvious question is, okay, fine, Paul, that looks really good, but does it work? So here I'm going to present our validation tests, and we've done 2 types of test. Firstly, we've compared the models against inundation extents. And we get those from a number of sources, from national and regional engineering flood hazard maps. So, for example, in the UK, we have a national 1 in 100-year hazard layer, and we can modelled hazard layer, and we can compare our model to the local models. You'd expect the local models would do a better job. So if we get close, we our global method should be okay. In some places, we've got really good satellite flood images, so we've done a couple of those. And in some places, we've got post-event reconstructions of maximum flood levels. And we're going to compare all those inundation extents with this CSI metric, which you can see in the diagram on the right. A CSI ignores, it's a pattern matching metric. And it looks at the ratio between the correctly predicted area in D, so the area of overlap, the union, the intersection, with the union of the two sets. And it ignores all the areas that the model says, the model and the data both say are dry. And we do that because that inclusion of area A biases these metrics, and CSI ignores that large, easy to predict area A and comes up with a really robust, difficult to match metric. So CSI obviously goes from 0 to 1, 1 being a perfect match, 0 being no match at all. And then for a number of places, we've got high watermark, so we can get mean absolute errors. And here's the result. So this is over a whole bunch of different test cases. And what you see are, let's look at panel A on the left-hand side. So this is the critical success index in version 2 and version 3 of our models. Version 3 is the open circles, version 2 is the crosses. So CSI is in higher numbers are better. So you would, and each column in this figure represents a particular test classified according to its return period. So you would hope that there was an improvement. The circles were going to plot above the x's, and you can see that in almost all cases that's the case. So where the original version 2 model was good, we have small improvement, but in some places we have really big hikes in performance as well. Panel B shows the mean absolute error, and here you want a lower number as possible, and you want the circles to plot below the crosses, and again they do exactly that. And you can see in panel C a sharpening of the error histogram for the water levels as well. Can summarize that across all tests. So the latest version of our models get an average CSI of 0.75 and a root mean square error less than a meter. And just to put that in context, root mean square error of the global terrain data set is we have about a meter of error in the global terrain data set. So this is about as good as we would expect to be able to do given the quality of global terrain information. And CSI of 0.75, that's approaching the skill of local models built with local data. So if we build a local model with LiDAR and known surveyed river channels and measured flows, if we compare that to a satellite SAR image, we'd get a CSI of somewhere between, anything over 0.7 you would regard as being okay. Anything over 0.8 and towards 0.9 you'd regard as really good. So the global model is approaching the skill of the local models we can build. And this is what it tells us about latest projections of global flood hazard into the future under different climate scenarios. So in this figure, I've plotted the annual flood volume in cubic kilometers. Okay, it's a weird metric, but trust me, this is a reasonable metric. So this is the annual flood discharge that we might expect as a global total. And you can see how this is changing out towards end century under SSP1 and SSP5. And the shading either side of these lines is the climatological uncertainty. So this is the one standard deviation based on the ensemble spread of the climate models that go into these estimates. So you can see that if you just look at the red lines at the moment, you can see that there's quite a big difference where we end up in terms of flood hazard based on the climate scenario. And also the uncertainty bands are, however, large and widen into the future. But at some point, we do conclusively diverge these two lines, and we can say, yeah, we are definitely not tracking on SSP1. And maybe by end of century, we will be able to conclusively say we are definitely tracking on SSP5. The lower panels show that, we're pretty certain about the coastal flooding increase because sea level rise is largely locked in. Pluvial flooding, more of the climate models agree on the sign of change here. So that's less, it's a moderate uncertainty. But we're really uncertain from current climate models in many parts of the world, even over the sign of change for river discharge. And that is reflected in the very wide uncertainty bars here. So here's the summary of that data. If we stay on SSP1, this is broadly the Paris Agreement targets. Median change out to end century is a very manageable 10%, and that's within the uncertainty in characterizing our current climate, which is somewhere about plus or minus 10%. Okay, there's a bit of a spread on the likely range, but it's not too bad. If we track, however, on SSP5, we could be looking at up to 50% changes in flood hazard, albeit within a large likely range. But changes of that scale are going to be much more difficult to adapt to. And it shows that mitigation efforts are still very much in play. Right, so just to finish up, I just want to digress a little bit into talking about catastrophe models. And first, a small introduction to those. So what I've been talking about so far are techniques to map flood hazard. They show for the whole planet what gets wet where. So they show the 1 in 100 year flood outline for the entire planet, or the 1 in 50 or the 1 in 500. That's a completely static view, and they don't tell you which areas are likely to get wet at the same time. So what's the probability of 2 areas within the country simultaneously experiencing a flood, or how many floods is a country likely to get in any given year? So these produce metrics of depth by return period, and they're good for visualization. What I'm going to talk about now are catastrophe risk models. And these show the spatially correlated financial losses. And so we draw on the maps, but to those we have to add an ability to generate large numbers of synthetic flood events with correct spatial structures. And here we're able to produce these results such as average annual losses and the loss exceedance probability distribution. So let's have a look at how that works. Well, the first thing that these methods require is an event set. So this is the spatial extent of a flood event and a map of the intensity of the event, probably in terms of return period, over that domain. And because we want to look into the tails of the distribution, we can't just use the spatial extent of events in the historical record. Because we want to simulate return periods of hundreds of years, we need many thousands of years of data in order to do this. And therefore, what we do is we build statistical models that can characterize the spatial extent of events from historical records. And then we use those to synthetically generate sets of many millions of flood events, all of which are plausible, but some of which may not have been seen in the historical record. Then we build in our hazard models, what I've been talking about so far. So here we take the physical intensity for each location for each event, and we sample that from our hazard layers that I've just been talking about. Then, to move to risk, we need 2 or 3 other things. First, we need global exposure data, so where assets are located and what their value is. And then we need something about the vulnerability of those assets. So if they were to get flooded, what would be the hazard the damage that would result? So we link the hazard metric to a damage ratio. And then lastly, if you want to go the whole hog, you might add some kind of financial module at the end, which insurers have these particular clauses. You think of it like the excess on your house insurance, which you might want to take into account. But that is, in a nutshell, how catastrophe models work. And what do they allow you to do? So this is a kind of a schematic of a CAT model. So these synthetic events are being generated across the planet. We're estimating the footprint, the intensity, the exposure and vulnerability. We're coming up with a measure of loss for these events. And these allow us to quantify the financial risk across all these flood perils that we've simulated, to understand how those risks accumulate in particular places, and how a particular set of assets that say a bank or an insurer might be exposed to those losses. And just to show you how this works, we've done this in the UK. We've built one of these models over the UK, and we've used it to look at current UK flood risk assessments. Now, we've got a number of those already. We have national flood risk assessments in the UK nations. We've got a national climate change risk assessment, and we've got, although these aren't not peer reviewed, we have catastrophe risk models in the insurance industry. And all of those things have limited or no method information in the public domain and limited or no validation. So we really wanted to change that, particularly because these are the observed flood losses that are collected by the Association of British Insurers. So this is the expected annual damage in billions of Great Britain pounds. The observed data suggests it's about 700 million, 0.7 of a billion pounds expected annual loss. But our main national risk assessments estimate that loss to be about 3 times higher. And this clearly cannot be correct. Could we build a model that does a better job of simulating the observed flood losses in the UK? That's what we've tried to build in this slide, and it's very similar to the flow diagram I showed before, so I'm not going to really go into it, but it's the same as the global model, but built with some local UK data. So it consists of input data, the hydraulic model, some climate projections, and lastly, this catastrophe model for building these event sets. And what you come out with at the end of the day are these risk metrics down here at the bottom. So this is what it looks like. This is some floods over Nottingham. It's 1 arc-second resolution over the whole UK, pluvial, fluvial, coastal floods. Mostly it's from LiDAR terrain. We simulate a bunch of return periods, include flood defences, and then we simulate these 10,000 years of stochastic flood events. And we drive them into the future with UK Met Office climate model runs. And finally, we look at the monetary losses, the loss exceedance curves for different specific global warming levels. And we'll have a look at those data. Anyway, first of all, here's the validation. So here's the vertical horizontal line shows the observed expected annual damage from the Association of British Insurers, and the other 2 lines out to the right are the current national estimates. The green histogram are 20-year bootstrap samples from our 10,000-year record of losses from the CAP model. So you can think of this as maybe current climate variability. We only have 20 years of observed data from the ABI. So instead of taking many thousands of years, we looked at the variation in 20-year expected annual damages that you could get under current climate. What you can see is that the modelled median of this histogram lies very, very close to the observed losses, and that's without really too much adjustment. So this is a genuine result. And you can see that the current risk estimates lie well outside the current model spread. So they probably are just as unlikely as they seemed. And this is the result we get for loss exceedance curves under different global warming levels. So to read these curves, this is return period on the x-axis and the loss that would be exceeded at that period. So the 1 in 10-year loss in present day conditions is around about 1.8 billion pounds. So here we are in 1990. This is our loss exceedance curve for with about 0.6 of warming since pre-industrial. And here's where we got to by about 2020. This is an extra ½ degree of warming, but really very little change in the loss exceedance curve for flood. And that's also the case if we stick to the COP26 pledges and all the net zero ambitions that countries have committed to. If the world goes down that path, then actually the flood risk increases that we see here in the UK are quite modest, and we could probably engineer our way through those. A very similar pattern to what we see at global scales. However, if we don't stick to our net zero ambitions, for example, if we just implement the COP pledges and we end up with about 2.5 degrees of warming, this century, then we start to really bend this loss exceedance curve. And if we end up above 3 degrees of warming, so for example, we miss all the carbon pledges and the climate turns out to be more sensitive than we thought, then we could see really quite large increases in 1 in 100 year losses. So here we are. This is the percent change in the 100-year loss in the final column with warming above 0.6 degrees. So from 1990, this plausible worst case scenario of 3.3 degrees of warming could result in nearly 40% increase in the 1 in 100-year financial loss. But if we stick to our COP26 pledges at 1.8 degrees, this is really much more manageable. It's probably within the climate variability anyway. But those are national figures, so they actually conceal very large variations in space. So in these plots on the left, you see the historical expected annual damage in thousands of pounds. And you can see that there are concentrations where the big cities are, most obviously. You can see a concentration over London, over South Wales, for Exeter, for the cities of the Northwest and the Scottish Central Belt, and the Newcastle area as well. In the figure on the right, we see the expected annual damage change with 1.8 degrees of warming. So remember, nationally, this would lead to quite modest increases in flood risk. But you can see that in some places, principally towards the west of the country and to the southeast, actually those small, modest headline changes in loss conceal quite big spatial variant changes that would be felt and cause problems in particular places. So again, cities of the northwest coast, South Wales, and the very densely populated southeast of England will see increases up to 25%, even if we stick to the COP26 pledges. Whereas there is a large band between southwest and northeast England, northeast Scotland, that will see negligible or even negative changes in their flood risk. So even if we control climate change, the geography of risk in the UK is likely to change into the future. And of course, this is just one set of climate model projections from the Met Office. And I think if we use different projections, we would have different patterns. But I think the overall picture of having to control climate emissions and strong changes in the geography of risk would remain the case. So to conclude and go to some questions, what I've hopefully showed is that we can now model global and regional flood hazard at unprecedented spatial resolution and accuracy. And this field has changed really rapidly over the last decade, and it will change more. It will continue to change rapidly over the next 5 to 10 years as well. There's lots of new data sets and methods coming through that will allow us to further increase the skill of these models. The outputs that we get compare very well to observations, almost as well as local modelling. And we're approaching local models and the error in the observations themselves. For future floods, we've seen both here in the UK and globally that the climate pathway really matters. Stick to the Paris Agreement, increases are pretty manageable. Miss that, and things get much more problematic. If we end up on SSP5, then that could be a real problem. And bearing in mind these headline figures, either globally or nationally in the UK, will conceal large changes in the geography of risk. We have less certainty over exactly how much flood risk will go up or down in particular places, but I think we're fairly certain that the geography of risk will change. Some people are going to be winners and some people are going to be losers, even if we strongly control climate emissions. And that's one of my spare slides. So I will stop there. And thank you very much for listening.